The Milky Way stretches across the night sky like a glowing bridge of dust and stars. To the naked eye, it seems calm, fixed, a grand river of light that has always been there. But when astronomers tuned their instruments to track every faint shimmer, the river began to break apart. They discovered a stream of stars flowing backwards, cutting across the galaxy's halo as if a current had turned against the tide. The paradox is sharp. How can a galaxy that rotates as one body contain a river that runs the other way? Observations from high-precision surveys confirm the defiance. This is no accident of perspective, no chance alignment. It is a scar, left behind by the swallowing of a smaller companion. A reminder written in orbits rather than stone. Standing under the arc of stars, you might imagine a family tree. Each branch is a cluster, each leaf a star. Yet here, whole branches seem grafted from another tree altogether. Their chemistry marks them as outsiders. Their paths tell us they were once part of something else, torn free and forced to circle a new center. In plain terms, our galaxy carries the bones of strangers, a home built from other homes. What kind of city are we living in if its foundations are half borrowed? And if we only now recognize them? What more is hidden in the glow above us? The mysteries do not stop at the halo. Our entire local group, the collection of galaxies that includes the Milky Way and Andromeda, is in motion. We are drifting through the cosmic sea at hundreds of kilometers per second, faster than expected. Instruments tuned to the faint microwave afterglow of the early universe revealed this drift decades ago, and every new survey confirms it. The contradiction is that while we can measure the velocity, we cannot find the captain steering the ship. The pull seems to come from a region cloaked by our own galactic plane, a place where dust and stars obscure our view. Instead of a single massive cluster, we find scattered knots of galaxies, none large enough alone to account for the motion. What hand is steering the arc of galaxies if no obvious object is there? Simply put, we are being pulled by something we cannot see. Imagine rowing in a fog, the boat sliding sideways despite your best efforts. You feel the current, you see the spray, but the source remains out of sight. Some astronomers argue that the effect arises from a combination of structures walls of galaxies, vast filaments, gravitational flows converging. Others say we are chasing a phantom, mistaking local variations for a great attractor. The data, however, keep piling up. Our drift is real. Our compass points toward a destination we cannot name. Why does the map of mass we have built not account for our own motion? And if we are wrong about our direction, what else have we misread? The final strand of this opening act comes not from the grand scales of clusters and streams, but from a faint radio whisper only 12 light-years away. A small red star, restless and stormy, sends out bursts of energy. Hidden within those bursts is a repeating signature that suggests interaction with a planet, not a gas giant, but a rocky world, perhaps Earth-sized, whose magnetic field clashes with the stellar wind. The collision releases radio waves, strong enough for our instruments to catch. If confirmed, this would be the first time we have detected the shield of another world across interstellar space. What this means is that survival itself may leave an electromagnetic fingerprint. If a magnetic field can be heard across the void, then the presence or absence of a planetary shield becomes a test we can apply to thousands of worlds. Could it be that habitability is not just about water and air, but about an invisible armor humming in the dark? In everyday language, the galaxy is whispering three stories to us at once. One is about a river of stars that should not exist, yet does. Another is about a current that pushes our entire neighborhood without a visible hand. The last is about a planet that may announce its existence not with reflected light, but with a hiss of static. Each story alone would be puzzling. Together, they confront us with a galaxy that resists any tidy summary. Why should history be written in scars instead of monuments? Why should the largest forces be invisible, while the smallest speak the loudest? Why should our best maps always reveal more absence than presence? At its core, This is the paradox of progress. The better our instruments, the less stable our story becomes. We build telescopes to clarify, yet they leave us more unsettled. A stream overturns our timeline of mergers. A drift undermines our catalog of mass. A signal redefines how we search for life. It is as if every attempt at closure opens a deeper loop. Some research groups present models showing how stellar streams can survive billions of years, marking mergers that shaped the disk itself. Others present data on galaxy flows, confirming that our motion aligns with large-scale structures only partly mapped. Still others test radio bursts against stellar activity, seeking to filter genuine planetary signatures from stellar noise. Evidence accumulates, but consensus remains out of reach. Think of it like this: if you stand on a cliff and look at the sea, you can see waves, tides, and perhaps the trail of a boat. Each signal tells part of a story, but not the whole. That is what we face when we read the sky. Stellar streams are the waves of ancient collisions. Galaxy drifts are the tides of structures beyond our sight. Radio signals are the trails of unseen worlds. We are learning to read all three at once, and the narrative they form is not a calm chronicle, but a restless testament. Does it frighten us that our home galaxy is unfinished, still shaped by forces we cannot contain? Or does it invite us to accept that incompleteness is the true shape of reality? Our journey begins here, with contradictions that refuse to dissolve. A scar in the halo, a tug in the dark, a whisper in the radio band. They are not accidents. They are signals that the Milky Way is not the finished portrait it appears to be. They compel us to climb higher in the watchtower of observation, to admit the map is incomplete, and to prepare for a journey where each answer will birth another riddle. Enjoy the unfolding search. Like and subscribe to the Quiet Universe channel. And if these three threads frame the opening act, the first to follow leads us into the ghost current winding through our halo. The night sky holds memories older than any civilization, but most are too faint to see with the unaided eye. When modern surveys began charting the motions of hundreds of millions of stars, a strange current emerged in the data. Against the overall rotation of the Milky Way, a group of stars traced arcs that ran in reverse. They were not scattered randomly. Their velocities aligned. Their chemical signatures matched. Their orbits formed a pattern like a ghost river carving through the halo. This was the Helmy Stream, an ancient scar left behind by the Milky Way's appetite. Instruments on Earth and in orbit confirmed that the stars in this stream carried chemical fingerprints distinct from the bulk of our galaxy. Their ratios of heavy elements resembled those found in smaller, primitive galaxies, not in the enriched disk of the Milky Way. In plain terms, these stars are refugees. They were born elsewhere, ripped from their original home, and pressed into service around a new center of mass. This is how we discovered that our galaxy did not grow peacefully. It feasted. It swallowed neighbors and incorporated their remains into its own structure. The contradiction is that for centuries we pictured the Milky Way as a stable spiral, a rotating island universe where stars formed and aged in relative peace. The ghost current tells us otherwise. Our home is a cannibal. It did not simply grow by forming stars from its own gas, but by stripping them from companions that drifted too close. What does it mean to live inside a predator that has been eating for billions of years? How much of our own sun's ancestry is tied to a meal long forgotten? Some researchers argue that the Helmy Stream contributes up to 1/10 of the halo's stars. That fraction is vast when multiplied across hundreds of billions of stars. It implies that the Milky Way's halo is a patchwork quilt, stitched together from many vanished galaxies. Each piece carries a slightly different shade, a distinct pattern of orbits, a unique mix of chemical elements. Simply put, the halo is not a smooth shell. It is a graveyard of swallowed systems. And if we can read its fragments, we can reconstruct a timeline of cosmic encounters. To put it another way, every star in the stream is an eyewitness. Their paths across the sky, mapped by satellites, show us the direction and violence of the merger. Their chemistry reveals the size and age of the original dwarf galaxy. Their very existence proves that the Milky Way is not closed or self-contained, but porous and dynamic. Some teams propose that multiple streams like this crisscross the halo, each one the fingerprint of a lost sibling. Evidence is suggestive, not conclusive, but the pattern is emerging. Our galaxy is not one story but many, braided together by force. In everyday language, the ghost current is like finding a river of bones beneath a city. You thought the foundations were solid, but then you learn the ground was built from older ruins. That realization changes how you view the streets, the walls, even your own house. Does it diminish your home, or does it deepen its story? If the Milky Way is a city, then its true identity is a composite, a mosaic of lives consumed and preserved in orbit. At its core, this discovery reshapes cosmology. Galaxies are not isolated factories of stars. They are shaped by collisions and assimilations. Each stream we detect becomes a data point in the greater theory of structure formation. By mapping them, we can measure how common mergers are, how galaxies like ours built their halos, how long it takes for streams to dissipate. Why it matters is clear. Without streams, we would underestimate the violence of the universe. With them, we see that growth is not gentle, it is ravenous. Think of it like this: if you saw a river cutting through a landscape, you would infer something about the past. The water eroded the land, carried away soil, left marks that endure. The Helmy stream is such a river, but its erosion is gravitational, and its marks are stellar. To follow its path is to learn about forces that act slowly but leave permanent scars. And as we uncover one stream, we realize there may be dozens more hidden in the data, waiting for detection. Micro questions rise naturally. If a galaxy can be dismantled and absorbed, what happens to its central black hole? Does it sink toward the core of the Milky Way, merging with ours? How many such mergers have already occurred? Are there dormant black holes scattered through the halo, relics of smaller galaxies devoured? If so, could they still flare under the right conditions, briefly revealing their presence? And if our galaxy is built on cannibalism, are we destined one day to be consumed by Andromeda, leaving our own streams scattered in a still larger halo? Why it matters stretches beyond curiosity. Streams allow us to test models of dark matter, since their shapes are distorted by the unseen halo surrounding the Milky Way. They allow us to reconstruct the timeline of star formation, since chemical fingerprints tell us when the swallowed galaxies lived and died. They even provide context for the origin of our solar system, which formed during an era when mergers were still reshaping the disk. Without streams, our picture of galactic history would be a blur. With them, it sharpens into a narrative of conflict and assimilation. Some evidence suggests that the Helmy stream is not unique, but one of many. Researchers using the Gaia catalog report multiple coherent motions, each hinting at another ancient merger. The details differ. The certainty varies. But the trend is unmistakable. Our galaxy's halo is a library of forgotten books. Its shelves filled with scattered pages we are only beginning to read. What other voices speak from these stars, and what new science will emerge as we learn to listen? The Helmy stream began as a contradiction. It now stands as a key. By accepting that our galaxy is not pristine, we unlock a deeper truth: the Milky Way is a survivor. Its beauty born from violence. The ghost current in our halo is not a footnote. It is a foundation. But if a single stream can reframe the entire story of our galaxy's origin, what will we learn when we turn to the meals themselves, the devoured dwarfs that changed the Milky Way forever? The story of the Milky Way's past is not only written in the streams that lace its halo, but also in the fate of the galaxies that collided with it. Among the most important was a dwarf galaxy devoured long before our species began to look up. When Gaia data revealed the Helmy stream and its cousins, another set of stars stood out. Their motions, compositions, and ages suggested they were once part of a much larger body. This ghost was nicknamed Gaia Enceladus, or sometimes the sausage, for the shape traced by its stars in velocity space. Whatever the label, the meaning is stark. Billions of years ago, a smaller galaxy crashed into the Milky Way and changed everything. The contradiction is that we imagine the disk of the Milky Way as an undisturbed cradle for star formation, slowly spinning and building its spiral arms in peace. The evidence says otherwise. Chemical analysis shows that many of the oldest stars in the thick disk have origins tied to the merger. Their compositions suggest they were either drawn in directly from the dwarf or triggered by the turbulence of the collision. Simply put, our home was forged in upheaval. A cosmic meal reshaped the very layers of the disk that cradle our sun today. In plain terms, picture a pond struck by a stone. Ripples spread outward, disturbing the surface and stirring the depths. The dwarf galaxy was the stone. Its plunge sent ripples through the Milky Way's gas, sparking bursts of star formation, thickening the disk and leaving behind debris that still circles above and below the plane. We live in the wake of those ripples, our own solar system forming later in a disk already thickened by the violence. To put it another way, our galaxy's graceful spiral arms are not just self-made ornaments. They are scars of impact. They tell of a time when the Milky Way doubled in mass almost overnight. Not by peaceful accretion, but by consuming a neighbor. The dwarf did not disappear quietly. Its stars, now scattered, continue to orbit in elongated paths that slice through the heart of the galaxy. Their orbits are not random. They trace the ghostly outline of the collision, frozen records of an ancient feast. Some researchers propose that this event occurred around 10 billion years ago, not long after the Milky Way itself had taken shape. If true, then the merger is not a side note, but a defining act. It may have set the orientation of the disk, dictated the growth of the bulge, and even influenced how dark matter settled into the halo. Others caution that the exact timing is still debated, the details uncertain. Evidence is suggestive, not conclusive, but the weight of multiple data sets points to a transformative collision. Why it matters is profound. Without this event, the Milky Way would not look the way it does today. Its thick disk, where many sun-like stars reside, might never have formed. Its star formation history would be quieter, its spiral arms less grand. The very conditions that shaped the cradle of the solar system are tied to the bones of a galaxy long gone. At its core, our home's identity is hybrid. We are children not only of the Milky Way, but of the dwarfs it consumed. Think of it like this. A family tree may look neat on paper, but if you follow it back far enough, you will find marriages, migrations, and adoptions that blur the boundaries. The Milky Way's tree is no different. Galaxies are families that grow by union and assimilation. To deny that is to miss the richness of the story. To accept it is to realize that our own sun may carry in its composition the echoes of a collision we never saw. The human-scale anchor is easy to grasp. Imagine a city rebuilt after a great fire. The buildings look new, but the street plan, the foundations, the materials all carry signs of the blaze. The Milky Way is that city. The dwarf galaxy was the fire. What rose afterward was different from what came before, stronger in some ways, scarred in others. We live in the rebuilt streets, never knowing the original skyline, but benefiting from the resilience that followed. Micro-questions rise naturally. If one dwarf could change so much, how many others have left subtler marks? How many star clusters we see today were seeded by the shockwaves of collisions? Could the conditions that made planets like Earth possible be the byproduct of cosmic violence? And if our sun's nursery cloud was enriched by material from a merger, does that make us, in a sense, descendants of another galaxy? Why it matters extends into the future. By studying the debris of past mergers, we refine our models of how galaxies evolve. We learn that growth is not steady, but punctuated by violence. We test the role of dark matter. Since the way streams and debris settle depends on the invisible halo, we probe the resilience of disks. Asking how they survive impacts that by rights should destroy them. Each answer sharpens the tools we will need to understand not just the Milky Way, but all galaxies. Some evidence suggests that the merger with Gaia Enceladus was the last major meal our galaxy consumed, though minor accretions continue. If that is so, then our home has enjoyed billions of years of relative calm since. Yet calm is relative. Another great collision looms in the future Andromeda. What we learn from the ghosts of dwarfs will prepare us to interpret the ultimate merger to come. Will the pattern repeat? Will our stars one day form streams in a still larger halo? The paradox remains. We live in a galaxy that grew by violence, yet that violence may have created the conditions for life to emerge. Our spiral arms, our thick disk, our halo all carry marks of assimilation. Without the meal, the Milky Way might be smaller, dimmer, less fertile. With it, we are what we are, a hybrid, a survivor, a host of many voices. But if eating a dwarf could alter the disk itself, what then of the strange pull that bends our galaxy's path, a drift that points toward a greater mystery beyond? From the time we first measured the cosmic microwave background, the faint afterglow of the early universe, an unsettling fact emerged. Our entire local group of galaxies is drifting. We are not sitting still in the expanding cosmos, nor simply orbiting the Milky Way's center. We are sliding through the void at hundreds of kilometers per second, like a raft caught in a current that has no visible source. The numbers are firm, the direction consistent. Yet when astronomers turn their telescopes to find what is pulling us, they do not find a single massive anchor. They find shadows, partial structures, half-seen clusters veiled by the Milky Way's own dust. The contradiction is sharp. Motion without a mover. We expect acceleration to have a cause, but the cause hides from our direct sight. Some call this convergence zone the Great Attractor, a region in the constellation Norma where our velocity points. But unlike a single star or cluster, the attractor is not something we can photograph neatly. It is not a single object we can circle with a red pen. Instead, surveys show that galaxies in a wide swath of the sky are flowing the same way, as if drawn toward a basin. Our galaxy is not unique in this drift. We are part of a larger flow, and the basin we move toward remains unclear. In plain terms, it is like being on a boat pulled sideways by a tide you cannot trace. You feel the motion, you see the shore recede, but the source of the pull remains hidden in the mist. Instruments confirm the direction, but each time we look for the mountain beneath the fog, we see only smaller hills. Is the Great Attractor a single mountain, or is it the combined weight of many unseen ridges? To put it another way, the universe is a web, and we are caught in one of its strands. Gravity does not always act locally. It builds over vast scales, stretching across hundreds of millions of light years. Flows of galaxies trace this architecture. Some research teams map these flows using redshift surveys, measuring how fast galaxies recede and comparing that to their positions. The results reveal patterns. We are not just being pulled toward Norma, we are part of a larger migration toward the Shapley supercluster and other massive structures beyond. Evidence is suggestive, not conclusive, but it appears that the Great Attractor may not be great enough by itself. It may be only the first step in a deeper current. Why it matters is immediate. Our motion relative to the cosmic microwave background is a key reference point for all astronomy. If we misinterpret it, we misjudge distances, miscalculate velocities, and misunderstand the distribution of mass in the cosmos. Our own drift is the baseline against which other motions are measured. If the cause is misunderstood, the whole cosmic map is skewed. In everyday language, it is like drawing a map of your city without knowing the true north. Every street you chart will be misaligned, every distance slightly off. The pull we cannot see is our missing compass correction. Until we understand it, the accuracy of every other measurement remains in question. At its core, the search for the Great Attractor is a search for hidden mass. Some argue that dark matter concentrations are at play, their gravitational pull felt but their presence invisible. Others stress that known clusters, like Norma or Hydra Centaurus, could explain much of the effect if fully measured. Still others say the Shapley supercluster farther out is the true basin, and what we call the Great Attractor is only a stepping stone. Competing interpretations, but all driven by the same undeniable evidence our galaxy is not moving the way it should if only visible mass counted. Think of it like this: a magnet can pull a needle even if the magnet is hidden under a table. The needle moves, the cause unseen. We are that needle. The cosmos hides its magnet in the zone of avoidance, the region obscured by the Milky Way's plane. Dust, stars, and gas make it difficult to peer through, leaving us to guess at what lurks behind. Yet new instruments, mapping galaxies in infrared and radio, are slowly lifting the veil. They reveal filaments and walls, long chains of galaxies stretching into the obscured region. Bit by bit, the outline of the attractor becomes clearer, though still incomplete. Micro-questions multiply. If the Great Attractor is not a single body, then what name should we give the force that drives us? Is it honest to call it an attractor at all? Or should we instead speak of flows and basins? What if our drift is part of a much larger cycle, one that cannot be understood from a local vantage? And if the Shapley supercluster is the real basin, how many other unseen giants are steering the web of galaxies beyond? Why it matters grows with every new survey. Mapping these flows allows us to test models of dark matter distribution. It allows us to understand whether structures form from the bottom up, with small galaxies merging into larger ones, or from the top down, with vast walls shaping the smaller nodes. It even affects our view of cosmic acceleration, since misjudging local flows could skew our interpretation of dark energy. Some evidence suggests that the pull we call the Great Attractor is already fading in significance compared to the pull of Shapley, our galaxy, along with thousands of others, maybe moving toward a still larger convergence zone, a supercluster of unimaginable scale. If that is true, then what we thought of as a destination is only a milestone. We are caught not in one current, but in a cascade of currents, each feeding into the next. Whoa. The paradox deepens. The universe expands. Galaxies recede from one another, yet we are pulled sideways, down into unseen basins. We live in an expanding cosmos, yet locally we drift toward collapse. These truths coexist, unsettling but undeniable. The cosmos is not a uniform tide, but a layered sea of flows and counterflows. But if the pull we cannot see shapes the course of our galaxy, then the next question waits at the edge of our maps. What if there is not only a basin, but also a wall, a structure so vast it redirects the rivers of galaxies themselves? When astronomers mapped the distribution of galaxies within 1 billion light-years of Earth, they discovered not only clusters and filaments, but also something more imposing: a colossal wall of galaxies stretching across the southern sky. This structure, called the South Pole Wall, spans over 700 million light-years, an expanse so vast that it dwarfs entire superclusters. What makes it startling is not only its size, but also its position. It lies directly along the path of our motion, as though the Milky Way and its neighbors are sliding along a current that ends at the foot of a cliff. The contradiction deepens here. For decades, we spoke of the Great Attractor, a gravitational anomaly hidden behind the Milky Way's plane. Yet the South Pole Wall suggests that what tugs us forward is not a single hidden giant, but a barrier of galaxies redirecting flows on immense scales. The discovery reshapes the map. Instead of falling toward a monster cluster, we may be flowing toward the edge of a continental shelf of matter, where currents converge and turn. In plain terms, think of a river running freely until it strikes a dam. The water cannot continue, so it spreads sideways, surging along the wall. Our galaxy is part of that flow, carried by gravity into a structure we cannot yet see in full. Why should such a wall exist at all? How do filaments and voids arrange themselves into boundaries of this magnitude? And if we are only now finding it, what other unseen continents of matter shape our path? To put it another way, the universe is not an even sponge of galaxies. It is more like a cosmic geography, with mountains, valleys, and cliffs sculpted by dark matter and gravity. The South Pole Wall is a mountain range. Its gravity catches rivers of galaxies, channels them, and alters their directions. Evidence from redshift surveys shows coherent motions aligning with this wall. The implication is that our local flow, once attributed only to the Great Attractor, may be part of a larger migration shaped by this continental-scale ridge. Why it matters is straightforward. Without mapping such structures, we misunderstand the architecture of the cosmic web. Our models of galaxy formation depend on knowing where the density peaks and troughs lie. If the South Pole Wall is as influential as data suggests, then it is a keystone in the lattice. Ignoring it would be like trying to chart Europe without acknowledging the Alps. Our distances, our flows, even our models of dark energy expansion depend on accurate local corrections. In everyday language, imagine planning a road trip without knowing there was a mountain range blocking the way. Your map would mislead you, your compass would confuse you, and your journey would make little sense. That is where we stood before this wall was charted. Now, the terrain comes into focus. Though only in outline, some sections remain obscured by the Milky Way's dust, hidden behind the glow of our own stars. As more surveys expand in infrared and radio, the full breadth of the wall will become clearer. At its core, this discovery underscores how young our cosmic cartography still is. We have only mapped a tiny fraction of the observable universe in detail, and already we find features so large they alter the motion of thousands of galaxies. What lies beyond? Deeper in the darkness, what other walls and ridges wait to be revealed? Each discovery reminds us that our neighborhood is less understood than we thought. Think of it like this: early sailors once believed the sea stretched endlessly, but then continents rose out of the mist, redirecting their voyages. The South Pole Wall is one such continent of galaxies, suddenly visible, suddenly undeniable. Its mass reshapes the journey of our local group, whether we acknowledge it or not. Micro-questions emerge. If such walls exist nearby, how many more stretch across the observable cosmos? Are walls and voids the fundamental architecture? With clusters only the bricks that fill them, could dark matter be arranged in these sheets, sculpting visible galaxies into their present positions? And if flows follow these walls, do they eventually lead to superclusters where collapse dominates over expansion? Why it matters reaches into philosophy as well as physics. We thought we lived in an expanding universe where motion was dictated by the global Hubble flow. Now we learn that local geography reshapes that flow. Our fate is determined not just by expansion, but by the contours of invisible ridges. This changes how we think about cosmic destiny. Are we forever sliding along the walls of the web? Or do we someday settle into their basins, trapped by gravity's hand? Some evidence suggests the South Pole Wall is part of a still larger structure linking to filaments that extend into distant voids. If so, it may not be an isolated wall at all, but a boundary of a greater continental plate in the cosmic geography. Evidence is incomplete, but the trend is consistent. The cosmic web is more intricate than we pictured. The paradox is that in a universe defined by expansion, we find local structures strong enough to deflect entire rivers of galaxies. We move outward with the cosmic tide, yet sideways with local gravity. Expansion and flow coexist, neither canceling the other, both shaping the story. But if walls and currents dictate the course of galaxies on these scales, then what happens at the very center of our own, where gravity is strongest of all and a ring of fire marks the domain of the black hole? At the heart of the Milky Way lies Sagittarius A, a supermassive black hole over 4 million times the mass of the Sun. For decades, it remained an abstraction, a radio source detected at the galaxy's core but never truly seen. That changed when an Earth-sized network of telescopes, linked together across continents, captured the first direct image. The result was not a pinpoint, but a ring of fire, light bent by the black hole's immense gravity into a glowing halo around a darkness that cannot be crossed. For the first time, we glimpsed the furnace at our center, and the sight was both a triumph and a warning. The contradiction is unsettling. Sagittarius A looks calm in the present, its appetite modest compared to the voracious black holes at the hearts of active galaxies. Yet the evidence from X-ray echoes suggests that only a century ago, it flared with violent brightness, lighting up gas clouds thousands of light years away. This central engine may be dormant now, but it is capable of waking in bursts that reshape the galactic environment. Our galaxy's core is not a quiet hearth, but a furnace that breathes in fits and starts. How many times has it done so before? And how many times will it again? In plain terms, imagine a volcano that sleeps for centuries, then erupts suddenly, coating the land in fire. The black hole is that volcano, its eruptions not of molten rock but of radiation and plasma jets. We orbit far from the core, safe for now. But the echoes prove that the eruptions happen, and that they alter the very fabric of the galaxy. To put it another way, the black hole is not an exception to the Milky Way's story but a central character. It governs the orbits of stars in the inner parsec. It shapes the flow of gas near the core. It may even regulate the growth of the galaxy itself. Some studies propose that feedback from these flares controls star formation in the bulge, blowing out gas that might otherwise collapse into new stars. Evidence is suggestive, not conclusive, but the possibility underscores the importance of understanding these cycles. Why it matters is clear. If we misjudge the behavior of Sagittarius A, we misjudge the future of the Milky Way. Black holes are not passive sinks, they are engines. Their gravity bends light, their energy heats the surroundings, their influence reaches far beyond their event horizons. The glowing ring imaged by the Event Horizon Telescope is a signature of this influence. It is not merely a picture. It is a confirmation of relativity under extreme conditions, a test of Einstein's equations in the strongest possible field. In everyday language, the ring of fire is like a clock face glowing at the center of the galaxy. The hands do not tick in minutes, but in bursts of energy and lulls of silence. When the clock flares, the galaxy feels it. When it sleeps, the galaxy grows in other ways. We are learning to tell time by this cosmic clock, but we do not yet know its rhythm. At its core, the paradox of Sagittarius A is that it appears small compared to the galaxy, yet holds sway over its dynamics. 4 million solar masses is nothing against the hundreds of billions of stars around it. Yet without the black hole's grip, the inner galaxy would unravel. We are tethered to a monster that grows only when it feeds. And when it feeds, the whole city feels the heat. Think of it like this in a metropolis. The central power plant may look unremarkable from the outside, yet when it surges or fails, the entire city reacts. The black hole is that power plant, hidden by dust, revealed only through signals that slip past the veil, the radio waves that betray its presence, the infrared flares that flicker and die, the X-ray echoes that light up the clouds. Each is a reminder that the power is there, whether quiet or active. Micro-questions abound. How often does Sagittarius A flare? Are these events tied to stars wandering too close? Torn apart by gravity, could smaller black holes spiral in, merging and feeding the central giant? If so, what happens to the surrounding stars? Could one day our galaxy's heart blaze like a quasar, reshaping the spiral arms themselves? And if the center governs so much, does it also set limits on where life can safely evolve in the galaxy? Why it matters reaches further. By studying Sagittarius A, we test gravity itself. The bending of light around the event horizon confirms predictions of relativity with precision. The dynamics of stars close to the core allow us to measure the black hole's mass with accuracy unmatched anywhere else. And the images of the ring link theory with observation, closing a circle long open in astrophysics. Some evidence suggests that the black hole is surrounded by structures more complex than we first thought: filaments of gas, magnetic fields threading the inner parsec, even hints of smaller companions. Each discovery complicates the picture. Each forces us to ask whether growth comes only from swallowing gas, or also from merging with other black holes caught in its gravity well. The paradox persists. Our galaxy is a spiral of calm arms and steady stars, Yet at its center burns a ring of fire that could flare at any time. We are both stabilized by it and threatened by it, tied to a fate we cannot fully predict. But if the black hole's growth depends not only on gas, but also on the mergers of smaller companions, then the next question leads us into the labyrinth of how black holes learn to grow. The portrait of Sagittarius A as a calm giant hides a deeper truth. Black holes do not simply exist, they evolve. They learn to grow, often in ways stranger than expected. For years, the consensus held that supermassive black holes increase their mass primarily by accreting gas, pulling matter from the environment and spinning it into a glowing disk before swallowing it. Yet models and observations now suggest that another process is equally vital. Black holes may fatten themselves by merging with their own kind. The contradiction is immediate. A supermassive black hole sits alone at a galaxy's center, but the galaxy itself grows by collisions. When two galaxies merge, each brings its central black hole. By rights, there should be thousands of pairs wandering their host galaxies, gravitationally bound, spiraling closer with each orbit. Observations have uncovered some candidates quasars with double peaks, galaxies with offset cores, hints of binaries waiting to collide. Yet these pairs are surprisingly hard to detect. The paradox is that theory says they should be common, but data still leave them rare. Are we missing them because they hide in dust, or because their mergers happen faster than we expect? In plain terms, it is like expecting to see construction sites everywhere in a booming city, but instead finding only a few cranes on the skyline. The growth must be happening, yet the evidence is subtle, fleeting, concealed. Gravitational wave astronomy promises to change this. As detectors sharpen, they will be able to pick up the ripples from black holes merging not just at stellar scales, but at galactic ones. When that happens, we will hear the footsteps of giants as they come together. To put it another way, the feeding of black holes is not a single-channel story. Some days they dine on gas clouds, steady and glowing. Other times they feast suddenly, tearing apart an unlucky star that wandered too close. And across cosmic timescales, they expand dramatically when two black holes themselves unite, releasing energy greater than all the stars in the universe combined for a moment. Growth is not smooth. It is episodic, violent, and layered. Why it matters is profound. Understanding how black holes grow tells us how galaxies grow, because the two are tied. Studies show that the mass of a central black hole correlates tightly with the mass of its host galaxy's bulge. The implication is that black hole growth and galaxy growth are codependent. If mergers fuel the black hole, they also stir star formation, spread heavy elements, and reshape the disk. To misread one is to misread both. In everyday language, imagine a heartbeat that keeps pace with breathing. One cannot change without the other. Galaxies breathe by forming stars. Black holes beat by consuming matter and merging. Together they set the rhythm of cosmic life. At its core, this research is a chase. Astronomers search for signatures of binaries in galactic centers, test models of gas drag that bring black holes together, and simulate how gravitational waves bleed away energy until the pair finally collide. Some simulations suggest that disks of gas act like labyrinth walls, forcing black holes into one another. Others argue that without such gas, pairs might stall for billions of years. The truth may vary from case to case, but either way, the labyrinth metaphor holds. Black holes navigate a maze of gravity, losing pathways until only one exit remains: merger. Think of it like this: two dancers whirl on a crowded floor. Alone, they might circle indefinitely, but the crowd presses in, nudging them closer, until they cannot help but embrace. In the galactic ballroom, the crowd is the gas, stars, and dark matter that fill the core. Their pressure ensures that what begins as a duet ends as a fusion. Micro questions come quickly. How many black hole pairs are hidden in galaxies around us? Could some lurk in our own Milky Way? Smaller companions spiraling silently toward Sagittarius A. When two black holes merge, how much mass do they keep? And how much do they fling back into the cosmos as waves? If mergers are common, Do they dominate the growth of giants? Or are they rare punctuation marks in a longer story of steady feeding? And when the Milky Way finally collides with Andromeda, will our central black holes meet, forming an even greater engine at the heart of the new galaxy? Why it matters expands beyond astrophysics. Detecting these mergers with gravitational waves will allow us to test relativity in regimes never accessed before. It will help calibrate the relationship between black holes and their host galaxies. It may even reveal populations of intermediate mass black holes, the missing links between stellar remnants and supermassive beasts. Each detection will be a lesson. Each ripple in space-time a new page in the manual of how black holes grow. Some evidence hints that Sagittarius A itself may have merged in the past. Its spin, its orientation, and the presence of warped stellar disks near the core suggest a complex history. Though uncertain, such clues hint at a restless youth. And if it grew by mergers once, it will likely do so again. The paradox is clear. Black holes seem like endpoints, final destinations where matter disappears. Yet they are not the end of growth but its engines. They learn, in a sense, to grow through feeding, through flares, through collisions. Their story is not closure but expansion. But if mergers and growth can be traced in gravity and gas, then perhaps the subtlest signals, the faintest clues, come not from mass at all but from whispers of radio waves, where a distant planet may betray its shield. Not all signals from the cosmos arrive in light. Some arrive as faint radio whispers, small bursts hidden in static. A recent case from a star called YZ Ceti, just 12 light-years away, suggested something astonishing: the possible detection of a planet's magnetic shield across interstellar space. For the first time, astronomers were not looking at light reflected from a surface, nor at a planet's silhouette crossing a star. They were listening. And what they heard was a rhythm that might be explained by the clash of a stellar wind and a planetary magnetosphere. The contradiction is that planets have always been discovered by their weight on a star or by the shadow they cast. They have been revealed through precision photometry and Doppler shifts, not by invisible shields. Yet here, data suggested that the shield itself, the invisible armor protecting a planet from radiation, might be what we detect first. Simply put, this flips the order of discovery. Instead of seeing a planet and then asking whether it has protection, we may hear its protection first, and then infer the planet. In plain terms, imagine listening to a storm through a radio instead of watching it through a window. The crackle tells you lightning struck, even if you never saw the flash. That is what researchers think they may have captured. The crackle was not random noise, not a passing flare. It repeated in time with a planet's orbit, as though the planet's shield were strumming the star's magnetic field. To put it another way, planets speak when they resist. Their shields create signatures that ripple through the radio spectrum. If we learn to read those signatures, we gain a new method for finding habitable worlds. A rocky planet without a magnetic field may lose its atmosphere quickly, stripped by stellar winds. A rocky planet with a strong field may endure, holding on to air and water for billions of years. If radio whispers reveal which is which, they become more than signals. They become filters for life. Why it matters could not be clearer. Our own Earth is habitable in part because its molten core generates a magnetic field. That invisible bubble deflects charged particles from the sun, preventing them from stripping the atmosphere. Mars, once wetter and warmer, lost its field early and slowly suffocated under the sun's glare. The difference between paradise and desert may be nothing more than a dynamo humming beneath the crust. If we can detect such dynamos on distant worlds, we can sort candidates for habitability more quickly than ever before. In everyday language, the idea is like checking whether a house has a roof before moving in. You could inspect the furniture, the plumbing, even the paint. But without a roof, the rest does not matter. A magnetic shield is the roof. Without it, a planet is exposed to the cosmic weather, and the odds of long-term survival drop sharply. At its core, this technique is still tentative. Some researchers caution that the signals from JWST may come from stellar activity alone. Red dwarfs are turbulent, prone to flares and eruptions that can mimic periodicity. The evidence is suggestive, not conclusive. More data, more repeated detections, more targets are needed before we can be confident. Yet even the possibility changes the landscape. Listening for shields becomes a project worth pursuing. Think of it like this. We have been looking for exoplanets in visible light, as though peering through windows. Now we realize there may also be doors, broadcasting and radio. If we can open those doors, we enter a new wing of the cosmic library. We no longer need to wait for a transit or for the tug on a star. We can listen instead, and what we hear may be the heartbeat of planetary cores. Micro questions spill out naturally. If we can detect one shield, how many more will we hear in the coming decades? Could radio telescopes catalog a census of planetary magnetic fields across the galaxy? If we find rocky planets without shields, does that confirm they are sterile, or could other protections exist? And if we find worlds with strong fields, does that make them prime targets for life, or only for further study? Why it matters stretches into philosophy. To hear the shield of a world is to glimpse its resilience. Life, if it emerges, does so not only because chemistry permits it, but because physics defends it. The shield is not life itself, but it is the fortress wall around life's garden. Knowing where such walls exist transforms the search for neighbors. Some evidence hints that radio detection of magnetospheres could also measure the strength of the field, not just its existence. If that holds, then we would not only know whether a roof exists, but whether it can withstand the storms of billions of years. That difference could separate fleeting habitats from true cradles of life. The paradox is sharp. We built telescopes to see planets, yet the first sign of habitability may come through sound. A hiss in the void may outshine an image. Our ears may succeed where our eyes strain. But if the shield of a world can be heard across light years, then the next question presses closer to home. What happens when a planet like Mars loses its shield? And how does Earth endure where its neighbor failed? Mars and Earth orbit the same star, drink from the same well of sunlight, and share many of the same raw materials. Yet their fates could not be more different. Earth is green, blue, alive. Mars is barren, dry, and silent. What separates the two is not distance alone, nor size alone, but protection. Earth has a magnetic shield. Mars does not. The contradiction is that both planets once looked more alike. Geological evidence shows that billions of years ago, Mars had rivers, lakes, perhaps even oceans. It had a thicker atmosphere, capable of holding warmth. In its youth, Mars may have been as promising as Earth, but as its core cooled, its magnetic field faltered, then failed. The guard was gone. Without that invisible armor, the solar wind tore at the atmosphere, stripping gases away into space. Water vanished. Surface pressure fell, and Mars was left a desert under the same sun that feeds our forests and seas. In plain terms, Mars lost its roof. Earth's roof remains. Imagine two houses built side by side, one with sturdy shingles, the other with none. The same storm arrives. One house stands dry, the other floods and collapses. That is the difference a magnetic shield makes. To put it another way, Earth's dynamo is a beating heart of molten metal. It powers the field that curves lines of force around our planet. Charged particles from the sun, guided by those lines, are deflected or trapped, creating auroras at the poles, rather than devastation everywhere. Mars once had a similar heart, but it cooled too quickly. Without a spinning, molten core, its shield faded. The storm had free entry. Why it matters is clear. If habitability requires long-term stability, then shields are not optional. They are essential. Life does not simply need a planet in the right orbit. It needs a planet that can protect its air and water for billions of years. Without that, life may start but cannot last. Mars may once have had the spark, but without the guard, it had no staying power. In everyday language, this is like lighting a fire outside. Without shelter, the flame flickers and dies in the wind. With shelter, the flame grows into a hearth that can warm generations. Earth is sheltered, Mars is not. At its core, this lesson changes how we search for life elsewhere. We cannot stop at measuring distance from a star, the so-called habitable zone. We must also ask, does the planet have a guard? Does it keep a magnetic shield, strong enough to last across geological ages? The answer will decide whether the world is a desert or a garden. Think of it like this. Mars and Earth are twins born to the same family, but one grew frail while the other thrived. The difference is invisible but decisive. Earth wears an armor of magnetism, and we walk in its safety. Mars went unarmored into the storm, and it lost its chance. Micro questions follow naturally. Could Mars ever regain a shield? Perhaps if its core were reawakened artificially. What would it take to build an artificial magnetosphere to protect a colony there? If Earth's field were to weaken, how quickly would our own atmosphere bleed away, and how many exoplanets we catalog today are already dead worlds because they lost their guards too soon? Why it matters stretches to our own survival. Earth's field is not guaranteed forever. Records show that it reverses, even weakens, over long cycles. While life has endured these changes, the future is not assured. Understanding how fields rise and fall tells us what to expect, how to prepare, how to measure the risk. The shield is not a permanent gift, but a dynamic process we must monitor. Some researchers propose that Mars's weak patches of crustal magnetism show what happens when a dynamo fails. Local bubbles of protection remain, but they are not enough to preserve the whole planet. Evidence is suggestive, not conclusive, but it warns us. A partial shield is worse than none, because it allows escape at multiple openings, while offering no global defense. Mars may be a cautionary tale written in red dust. The paradox, then, is that life depends on what cannot be seen. We praise oceans, mountains, atmospheres, but the true guardian is invisible lines of force. Earth's shield bends storms into auroras, turning danger into beauty. Mars' absence of a shield turned promise into silence. Our own survival is tethered to a process hidden beneath our feet. Molten iron spinning in darkness, never seen yet always protecting. But if Mars shows us what is lost without protection, and Earth shows us what is possible with it, then the philosophical echo must ask, in a universe where survival depends on unseen guards, what kind of story are we truly part of? The tale of our galaxy has been told in fragments. We followed ghostly rivers of stars that carried the memory of galaxies long consumed. We traced the currents that pull us toward basins we cannot see. We stood before the vast wall of galaxies, its gravity redirecting rivers of matter on scales too large for the human mind to hold. We looked into the ring of fire at our own center and considered how black holes feed, collide, and grow. We listened for faint radio whispers that may be the shields of distant worlds. And we compared two siblings, Earth and Mars, one with a guard, one without, and understood how survival rests on something invisible. These stories are not isolated. Together they form a single arc, a portrait of a universe where identity is written not in permanence, but in change. The paradox remains constant. Our instincts seek stability, yet every clue reveals flux. The Milky Way is not a monument. It is a process. It eats and is pulled. It shines and it flickers. It builds shields and it loses them. Even the ground beneath us, the magnetic armor we depend upon, is temporary. A dynamo that may falter one day. The lesson is stark. To be alive is to inhabit instability, and to persist is to learn how to read and adapt to it. In plain terms, the universe is less like a painting on a wall and more like a river, The painting appears finished. The river is never finished. It is motion itself, and we are drops in that river, carried whether or not we understand the current. Some researchers suggest that our own solar system's birth was tied to a violent period of mergers in the galaxy, when streams of foreign stars and clouds of gas reshaped the disk. Others note that the chemical makeup of Earth hints at enrichment from ancient supernovae triggered by such events. Evidence is not absolute, but the implication is clear. Our planet's possibility, and therefore our existence, was a consequence of cosmic collisions that would have seemed destructive at the time. Life is not separate from violence. It is one of its outcomes. To put it another way, the cosmos is not hostile, nor is it benevolent. It is indifferent. Yet in that indifference lies the very stage upon which complexity arises. A black hole flares and silences, and in the spaces between, stars are born. A planet loses its shield and dies, while another keeps it and flourishes. A wall of galaxies bends the motion of thousands, yet inside one of them, minds awaken and ask what it means. Why it matters is not only scientific but existential. When we map the sky, we are also mapping ourselves. Each discovery of a stream, a drift, a flare, a whisper, a shield, becomes a mirror. The galaxy is telling us that we are temporary, yet not trivial. We are woven into its contradictions. Our lives are measured in decades, but they are framed by processes that last billions of years. To live in awareness of that scale is to inhabit both humility and awe. Think of it like this, standing under the night sky. We are not outside the story. We are inside it, carried along. The same invisible pull that tugs the galaxy drags us. The same black hole that binds the stars binds us. The same shield that protects Earth allows our breath. The same silence that haunts Mars warns us. The universe does not speak in words, yet every stream and every signal is a sentence, every wall and every whisper a fragment of a greater text. At its core, the philosophical echo is simple. We have been asking, where do we come from? The universe answers not with a single place, but with processes: merger, flow, flare, erosion, protection. We are made by all of them. We are fragments of streams, passengers in flows, children of shields, and heirs of flares. One paraphrased line rings strongest when the map changes. The truest question is not where are we, but which current do we follow? The closing image lingers. Imagine the Milky Way arched across the night, its halo stitched with ghost currents, its disk sliding toward a hidden basin, its center glowing with a ring of fire, its outer reaches whispering with faint radio storms. In that immensity, Earth circles quietly, wrapped in a shield that hums unseen, keeping oceans liquid and skies breathable. Above our heads, the aurora shimmers, a reminder that the invisible guard is real. Beyond, Mars turns silently, its story written in absence. Farther still, planets we have never seen may call out in radio whispers, their shields humming their own defenses into the night. The question that remains is vast and unanswerable, yet urgent if survival depends on currents we cannot control and shields we cannot always see. Then what kind of future do we choose to create within a universe that has never promised permanence?